time to get started. It is my real pleasure to introduce today's special speaker, special time, Peter Kareiva, who comes to us from the Nature Conservancy, TNC, where he is chief scientist and vice president of science for the Nature Conservancy. So, Kareiva's name is pretty well known to an awful lot of people in the sort of global conservation community. He's worked across a wide variety of different kinds of jobs and different experiences in university, government, and currently the NGO world. In terms of his academic background, he received his, to get this right, his undergraduate degree at Duke, his master's at UC Irvine, and then his PhD at Cornell in ecology and evolution. He did in there a brief stint as a lecturer at CSU in LA, so he's worked a little bit in and around Los Angeles a while back. And when after he finished up, he took a position for 5 or 6 years at Brown, where he was an assistant professor, and then moved to the University of Washington, where he was for a dozen years as an associate full professor. And he left UW, worked for fisheries for a few years, and then in the early 2000s moved to TNC, where he's been ever since. And if you look at Peter's, as I did today, so look through his CV and look at his papers, they plot a really interesting trajectory. So when he first started at Brown and UW, it was all of this really mathy, really nerdy, sort of population biology work. And somewhere in the middle of that UW period of his life, you started seeing these funny kind of shifts in the papers, the titles of the papers. And it was sort of, it was mathy, nerdy stuff, but it was about invasive species, or it was about sort of some aspect of conservation biology. And conservation science started kind of creeping into his work. There was work on GMOs, there was work on invasive species and what to do about them. And that theme has kind of increased throughout his career, and obviously it sort of accelerated after he moved to the Nature Conservancy. He's worked on and continues to work on a really wide variety of academic and applied issues very, very broadly across the spectrum of conservation biology. He's worked extensively with biologists, he's worked with economists, he's worked with and collaborated with people in the sort of environmental literature world, all kinds of different sorts of folks. Always with a little bit of an edge towards sort of looking at especially recently, the role of people and sort of people and conservation and environmental conservation, and how people increasingly do or do not play well with the conservation movement. As many of you know, much of Peter's work is interestingly controversial, and especially that work looking at the interplay of humans, environmental issues, and conservation science writ large. So it's a real pleasure. Well, I guess it's not the title. Maybe the title is. Where did I go so terribly wrong? You got that?
That's about right. Is that good? People in the front sleep is being looked at. So you almost you were befuddled with my career, so am I. It's not an arc, it's not a line. It's an arc with me coming back to academia. So I want to tell you, I'm going to tell a little bit about my very applied work and where I've ended up now in sort of the theoretical and sort of some of the more academic questions I'm interested in. Although I will always have an interest in the environmental community and activism and policy and so forth. Shortly after I left University of Washington and I was at NOAA, I went and gave a seminar at Duke University, and I won't say who on the faculty, there was a close friend of mine from graduate school, and I gave a seminar about salmonids, endangered salmon, and he said, "What happened to you? You used to do such interesting work." I thought, and I said, "It's a midlife crisis, I'll get over it," that's what I told him. But, and I was primarily a mathematical modeler, dealt with species interactions, well, always with a spatial dimension. So that was there was consistently a thread of explicitly dealing with space in the models. And that was my niche in mathematical modeling. I also did a lot of empirical work, field experiments at the same time. So how I initially got into this field was teaching a course in patch models, patch theory, classical patch models, and some of the students were interested in conservation and then moved to saying, do patch models and metapopulation and spatially explicit modeling have anything to do with spotted owls? And there was a whole series of trials with spotted owls. And this is an interesting case where some of the basic insights of simple undergraduate ecology insights from theory actually mattered. And here's the argument that the Forest Service and the industry made about spotted owls. We can go to old growth forests in Oregon and Washington and find patches of old growth that have no owls. Therefore, there's a surplus of old growth habitat, and therefore we can cut old growth habitat. Well, if you don't even know the simplest metapopulation or models where there's turnover and so forth, there's always going to be empty patches. In fact, there's empty patches does not speak to that you cut the old growth. But that was a pretty convex, that was fun. And that came up in the court case. It was very much in the court case and the testimony with the federal judge. And then in the middle of the midlife crisis, I got hired by NOAA to lead their conservation effort related to salmon. And really almost all the science was on Chinook salmon in the Snake River and the Columbia River and its tributaries, because it was listed and it's a nexus of conflict between agriculture, which is water for irrigation, between shipping down the river, between dams for hydropower, between tribes, between commercial fisheries, between recreational fisheries. So it's a real hotbed of conflicts around single species management. And it also becomes a very symbolic battle around about should we take out Snake River dams. And they want to take out, frankly, the environmental community wants the dams out for a wide variety of reasons, but they use the Endangered Species Act and this single species of salmon as the lever by which they would do it. And there was a lot of extinction modeling. I knew how to do this. My grad students know how to do this since I go over grad students because I was in NOAA. But there was such uncertainty. This is a full-page ad in the New York Times, and it says if we don't take out the dams, without prompt action, wild Snake River spring Chinook salmon, once the largest one of the kind in the world, will be extinct by 2017. I used to give town hall meetings and say, I'll bet any of you my house. Because I knew that there's no uncertainties data there, and I knew the data well enough to know that wasn't true. Because the dams, dams aren't coming out pretty soon, it's 2017. And there was, this just was ridiculous. But it was interesting to see the models in there. Talk about big science. Spent almost $250 million funded primarily University of California professors, UC sister professors, to do modeling of salmon. And the models they used to, you could be doing them for the tribes, you could be doing them for the fisheries industry, you could be doing them for the Bonneville Power Authority, and so they were competing models. That's what happened. Is a very, very rich modeling effort, informed by very expensive data to collect because they could pick tag the salmon and build up a database that looked at the fate of individually identified fish as they went down the river, out of the ocean, and they came back in. So, like for a population biologist model or terrific database. But look at that. This is not for, there's a huge budget for restoration. This is research money. This is not conservation activity. This is research money, $250 million put into the model. And I came in, and I remember I knew nothing about salmon except to eat it and cook it. But sure, I think it might have been my second day on the job, and we had money from Congress to hire a lot of people, so we could hire a number of scientists. There were all these reports from these models, and it's not an exaggeration to say that the reports stacked this high. And they said, read them, figure out what they tell us, because you got to testify to Congress and CEQ. And so I just dove into the models. So they called them, I can't find any lecture, I think they've erased the digital history of this, because it's kind of embarrassing. Their model had 150 variables with 500 plus parameters. It was impossible to penetrate. And what I learned by reading the appendices, this was just amazing. You can go back and check, you're not going to believe what I'm about to say, because it's going to sound pretty unbelievable. All the results of the model were couched in terms of meeting recovery goals, or failing to meet recovery goals, which were set up by policy and worked heavily with the legal team. And so all the results of the models, the competing models, the models that were saying the dams had to come out versus the models that said they didn't have to come out, models that said you could fish versus you couldn't fish, they all were couched in terms of recovery goals. What percentage of the stochastic simulations meet the recovery goals? I went and asked, because like any good population biologist, can I just see the data on the populations? You know, because ultimately all this, what's the data in the populations? No matter what set of parameters, no matter what assumptions, every model output had the salmon increasing exponentially. So every single one of the actual raw data, looking at the population output, had the salmon increasing exponentially. It had gotten so obfuscated in this morass that, nobody, somehow that got beyond. So I did a simple model, we got it published and all that. The data comes with putting pit tags in, and I think I'll skip through this. You just build a simple model that has maybe 6 parameters that you can really estimate and understand, stage structure, population model. And, we came to the conclusion that taking the dams out wouldn't do any good. It would do some good, but by itself it would not recover the salmon. Our model showed, when we analyzed the model, it showed the population declining. So we had lambdas, intrinsic rates that were decreasing in some places, and this was not going to solve it. I moved from there to, I had a friend who was a grad student. I took a graduate seminar from me at the University of Washington. His name was Walt Reed. His thesis was on Arctic seabird behavior and reproductive behavior, classical behavioral ecology. And he went to WRI, became vice president of WRI, now he's head of the conservation program at Packard. But in the intervening period, with help from primarily Hal Mooney at Stanford and Bill Ruckelshaus, he led the Millennium Ecosystem Assessment, which also had a ton of models in it. And these were models, Walt's idea was to say, we as environmentalists and conservationists, we're not making an impact. We have this whole global climate change stuff and IPCC and all their reports, and their science is getting into the policy arena. Ours is not. Our science is silent. And partly because it's just biodiversity. So let's talk about ecosystems and ecosystem services. And there are over 1,000 scientists involved in it. The real genius that Walt did, they funded a lot of international postdocs. As is often the case, the postdocs did all the work. And, but they did some very good work. My job was to come in and write the modeling chapter to review, partly because I had done this for salmon, and Walt knew that, is to review all their models and ask, how credible they are. And I learned a lot from that. They were not anywhere near the same league as half models for the salmon. These are some pretty credible models, although still very hard to decipher. Coming out of that, though, the message from that was the world's going to hell. Because ecosystem services are, through human impacts, ecosystem services are declining at a global level. Something like 2/3 of ecosystem services are declining. That was what the media put out. That was the narrative. That was the message. You can't do anything with that. It doesn't lead to solutions. So you've just told yet another story about the world's going to hell with your models and some data. What do you do with that? And then it got a lot of press. The other message is these ecosystem services have economic or somehow tangible real value to humans. And you could put a dollar value on it. And if you did that, it would save the planet. Now, there actually wasn't much data or science to support that. It was a claim. There wasn't really, it was a lot more of this than, that's our rate, by the way. There was a lot more of that than it was really solid data to show that economic or local impact of that. So that's what I committed, the last 7 years of my life to start working on scientifically. And we formed what's called the Natural Capital Project, and we developed software models. I'm going to talk a little bit about the modeling philosophy, the theory, and eventually you'll see where this has gotten me to now. But there the idea was, these global models are great for stories, but decisions are made locally. And what you really need to do is develop models and easy-to-use software for decision makers, and you have to validate them and all that sort of stuff, that give you information that if I do this, this is going to happen, and if I do A, this is going to happen, if I do B, something else is going to happen. And it's nice to put dollar values on it, too, to speak to certain constituencies. So, no longer global models, all very local, sometimes at the size of large property values, maybe a watershed, maybe watershed associated with a city, maybe a model at the scale of an area where mining is being done, things like that, different scales, but not really tiny scales, but certainly not continental, not even really whole country scales. A little bit of whole country in China, but not really. So the way you learn to do the modeling is there's always a danger in these big ecosystem models and these types of exercises that you can write code and generate output, but it never confronts reality. And you can build up these very elaborate computer pictures of things. And so in this case, all the model development was done in particular places. And then you try to generalize as best you could and make the parameters. So one of the early decisions, which is interesting, was there's two paradigms for generating this ecosystem valuation when you do this modeling. There's still not much of it that's very good, but they're basically benefit transfer versus what? Production functions. So there's two different ways of collecting information about the performance of ecosystems and trying to turn that into monetary value, because the theory of change is that if you can turn it into monetary value, you can influence policy. And so we made an early decision, and the early decision was to reject out-of-hand benefit transfer. So if you know the papers by Robert Costanza, most cited paper in our field in Nature, 1997. I could add everybody in this room, in this department, and all their citations up, multiply them times 10, and it wouldn't be cited as much as Costanza's paper. And a huge paper about it came up with, was it $33 trillion, Nature was worth $33 trillion for the world. But the way benefit transfer works is it's essentially a lookup table. You have good empirical work that collects information about, it might be a southern hardwood forest, and that hardwood forest purifies water, and because of that you don't have to put in an engineered treatment plant on a potato chip fab. And you know how much that it would cost you to treat the water, so you say that's the value of the hardwood forest. It has a certain number of acres, so it's got a value per acre. And so there's different empirical studies that are done that way, but then you generalize them. Then you take these empirical studies, and there are values per acre, and you just, it really is an Excel lookup table. It's an Excel lookup table where habitat has this value because you've done some empirical study. That did not, you could do it quick and cheap because it's really mining the literature. And you could fudge it, you could use a little bit of ecology and sit there and say, well, we're going to have a scaling factor, kind of a fudge factor, that, oh, okay, this acre isn't, you could adjust it. So I'm being a little unfair, but not too unfair. So, we rejected this. And we rejected it, and partly because of my background in spatial stuff. When you do benefit transfer, the landscape doesn't matter. Doesn't matter how, if you have 100 acres of hardwood forest or 1,000 acres of hardwood forest and you want to know the value of water per purification, it's the same per hectare. But you know from functions, hydrology and so forth, that it's not. And there's no sense of context or even configuration. If you have 1 acre here and 1 acre over there, that's the same as having the two together. Well, it's not. It's not. So it can't handle that. So I mean, I spent the first 20 years of my academic life thinking it's the spatial distribution of organisms and habitats mattered, and here's this machinery that just ignores it all. So we went for the production functions, which is actually running dynamic models that track hydrological processes, filtration, carbon uptake. They're ecological models is what they are, like ecosystem models. But it's very popular. The benefit transfer produces statements like this. Costanza's group did one for New Jersey, for the state of New Jersey. It said, you know what? Your natural habitats generate $19.4 billion per year by doing this benefit transfer. Getting the acres in these natural habitats, getting a dollar value per acre, summing it for the state, saying this. And to me, that's, it gets newspaper headlines, but it's actually just not useful. What do you do with that? You just say, well, nature's value. Okay, I already knew that. And most people already know that, frankly. There's no. So we started building modules. The other decision, there are other competing models out there that I would call our whole ecosystem models. We did not do that. We took one function at a time. Because we always had clients and decisions. So it might be like, the most popular functions by far are water supply, storm surge reduction for coastal habitats, and water filtration, taking out nutrients and pollutants. Almost no demand for any other ecosystem services when you go to real decision making. So we built, the other sort of interesting decision we made is to build everything modular. To build it modular, so you created a consistent data format for which data would be entered, land use, land cover data, and you could have it at different resolutions depending on your database. But to have that data, we overlay climate data and some hydrology data, soil or whatever, but a consistent format for entering data, but having modules so that you might be only interested in flow, water flow, or what's called water yield. You might only be interested in taking nitrogen, or different things, or storm surge. And each one of those, because it's not a lookup table, to develop just one of those models takes a postdoc, at least one postdoc or two postdocs, 2 or 3 years. That's the difference between it and the benefit transfer. Just to develop the model in one place. And then you have to start applying it in other places to get a sense of how to generalize it. But that was our approach. And you can look it up, the software now and invest, it's all freely available. I think that was a smart approach. First of all, we supported a ton of postdocs, maybe 40 or 50 postdocs at least, at Stanford, maybe Stanford, University of Minnesota. Supported a ton of postdocs. They could own it, because they could own a process. Often they had to work in teams. So for the coastal surge, we had to have an ecologist, salt marsh expert, and then we had to get a civil engineer specialized in oceans, civil engineering together to do it. But it lent itself to some sort of individual creativity and control and doing your own research, but plug it into a bigger picture. We always had the vision of what we started off with what we call tier 1 modules. The other thing we realized, because we had some practical experience, is that you don't build one model, you have different tiers of complexity. So what we started with tier 1. Tier 1 meant you could probably get the data to do this anywhere in the world, including Africa or Latin America, not just the US. Tier 2 would be that's not the case. Tier 2 is usually pretty much US data or Europe data. And then tier 3 is really at the research level. And early on, we thought we'd never gotten to a tier 3. That just as an aside, because there's just no demand for it. We actually had a demand for what's called tier 0, which is even simpler than we felt comfortable with. That's probably what's most used by a lot of our clients, if you will. We do tier 2. Tier 2 is needed when a real specific decision is made, almost like a design decision. And I'll show you sort of the level of detail for tier 2. These are the these are like the initial rendition of the modules: recreation, flood regulation, climate regulation, wood fiber, freshwater, agriculture, pollination, etc. We ended up never filling in all these boxes, and in response to like a model that we haven't developed yet, but there's a lot of appetite for, is fire risk reduction. How do you manage habitat for fire risk reduction? And what's the value of different management things? We haven't developed that yet, but it would be great to be a postdoc to do that, this modular system. And so you get this input, the stakeholders or our clients want to look at particular scenarios, choices about what to do in a coastal area or fisheries or whatever. And they are interested in only some functions. They're not interested in the whole ecosystem. They pick what they're interested in. We have modules that deal with that. We might have to invent a new module, in which case they have to pay for the postdoc salary. They have to pay for something no matter what. It's about physical output and then economic output, dollars outputs. This is how we actually display the data for land use decisions in Hawaii. For private, where you had total control over the land, and the real decisions were biofuels, subdivision, or sort of agroforestry, light impact sort of resource extraction for the land. And what would happen to these services they were interested in: carbon storage, water quality, water yield, and income. And this is actually, there are numbers behind this, but we actually presented it to them this way because that reflects the caliber of our precision in the model. And we didn't want to be dishonest about that. Interesting stuff, but I'll say one thing. We've never been told to get $1 bottom line. And now we've done 24 series of applications. They want us to do the economic valuation, but they don't want a bottom line answer because they can actually, their decision makers are smart enough to balance things. That was something we learned for doing the project. We employed a lot of economists and postdocs. But an example of the tier 2 model, and some of the results that were published in Nature Climate, is actually, real concern about with rising sea level, severe storms, and what happens to coastal property. So most of the world's population lives up near the coast. A lot of property values near the coast. Habitats, oyster reefs, and marshes, reduced storm surge. That's been known for a long while. Can you turn that into something? Can you actually model that and not just have it be a nice story, but turn it into something? So, and this is where we get the engineer, the coastal engineer. You actually model the wave height. You model the actual structure of restored oyster reefs. The structure means how far across they are. You measure that. How high they are. That all goes into it. You could be doing this for salt marshes. Very, very explicit model. And then you look at how much that reduces a 100-year storm and then the property damage. That's a pretty detailed model. And you use it to design. This is the model that you use to design oyster reefs. Because when you restore oyster reefs, you have a lot of options. And then you can put out oyster reefs. This is kind of a cool picture because you put out oyster reefs and see how they work in terms of what they do to the coastline. And, at a national policy level, what you do is you do the experiment. Once you've got the models up and running, you do an experiment and say, what happens if we lost all our natural habitat, all the shoreline natural habitat that currently exists? How many different people would be at high risk of hazard, serious life hazard? And you can tally it up by states and say, if you lost all your habitat, you're going to put an extra 20 million people at risk. And then you can go to particular areas, and then you have to fine-tune the model. So that's pretty effective use of a model, of a tier 2 model. And, it's really hard to validate these types of models. So you do things and test them, especially things like mortality. So for that particular case, you look backward and predict a rank ordering of fatalities due to severe storms and see if you're by state, you've predicted that right. And you do pretty well. That's pretty well for backward prediction. So there's observed mortality in 21 states that you predict as a function of how much natural gas you have and your modeling of the storms. But then, thinking about this more, the way this modeling works is options. Improve, irrigate, and food crops or biofuels. Or don't do anything and keep the system as it is, or residential development. And what the model really, all these models really do is they change the input data in terms of land use, land cover. And these different color codes are land use, land cover classes. And the actual scenarios are changing land use, land cover classes. And associated with each land use, land cover, there's some parameters that govern the dynamics of the model. So that's what it is. Then folks, almost everybody nowadays says, what about climate change? Our classification systems for land use, land cover are kind of rigid in many cases. And you start thinking about it. And everything really flows from land use, land cover in these situations. With the next postdoc of mine, who's become sort of a leader in Argentina and Patagonia, Miguel Pascal is his name, I sort of had an appetite for getting back involved in a real place. And Miguel's a good colleague, he's got a great group around him. So I got involved in applying some of these models to Patagonia in a more of a research way. So it wasn't quite so tied to clients or government decisions existing. So we're to really, really understand them and get the models better, so maybe a little bit later they could. And what we did, in Patagonia, it's not just water, it's desertification. Because grazing is a big deal in Patagonia, and how intense the grazing is can shift to overgrazing and really desertify the grasslands. So it's water and desertification. And we tested the models, I'll show that. But here's how we started thinking about it, and this is just work that's I spent 2 weeks with Miguel about rethinking about how to do this modeling. This is what we want to do next. Is when we're doing a sensitivity analysis and we're classifying the vegetation and we're doing the climate change, we realized that all the models we're working with, topography, climate, soil, and you have these land classes, but they're really arbitrary. They aggregate things. They're kind of weird. Anytime you go to a real place and look at land use, land classes, there's always a little bit off. Because the boundaries by which they're defined are always a little arbitrary. But from these land use, land classes, you get biophysical models, and then you get your outputs. And that's pretty much all the ecosystem service models. So the benefit transfer does it this way, and so does the ecological production function do it this way. They really use remote sensing land use, land classes. We thought the data are getting better. We know the technology is changing it, and we have an opportunity to not be so wedded to these arbitrary classifications and try to go back to first principles and maybe think about building the models by more directly measured parameters where they don't force you to go into land use, land classes. They could be particular species which you can identify. They could be presence and absence of particular species. Better data on soil types, getting information on groundwater. So depending on the process, instead of forcing all the models to go through a land use, land class filter and having it drive it, let's not do that. Well, we haven't built these models yet because it's a new machinery. But that's what Miguel and I want to spend the next couple of years doing, because we can get the data. We've got a really good team of researchers. And because I think it's the future. It's the future because of the technology. And so we might end up with, like, in the climate, when we think about Patagonia, these are sort of the soil, climate, topography, vegetation, water. Large herbivores are a key thing that you want to track. You single out the large herbivores because of your ecological understanding. And that's not a land use, land class, but it's important to the dynamics. So that's sort of the different thinking. But the reason why is this, one of our partners is Digital Globe. They put out they get their money from defense, basically, so all the defense top secret stuff. They have really good resolution. Commercially, you can get 40 centimeter now, actually 30 centimeter. You can get, militarily, you can get lower than that, but they won't allow you to use it. So for our purposes, it's different, but for military, you get lower than that. They can produce really fine-scale images, and you can start using those images to do really interesting things. The other thing you can do, which we ran a trial, I did not run this trial, but we're going to try it in Argentina. TNC ran this trial in Orion. Is this private company has a crowdsourcing platform. And so we were interested in invasive species, Australian tree fern, and because you wanted to control its population spread, and you wanted to get really good data, cheap, fast, you could measure this for everything. They use this for human slave trade, they use it, you could use it for poaching on elephants. But, so for this particular Hawaii application, we had almost 3 million different images, and each one was viewed by 100 volunteers to look for the species for free. For free. There's a whole community out there of really young kids that love to do this. Amazing. So we think, looking forward for these types of ecosystem models, that this is the caliber of data you're going to be able to have. Not land use, land class, which are sort of the spectral properties, but much better information. And it's that feeling that let's start building the theoretical machinery to handle it. These are amazing. This community, it also engages you in the environment. We did follow-ups. I mean, when people participate and feel like there's a solution to the problem, they really love it. I mean, they really like doing this. It doesn't cost a penny. All free volunteers. They use this, this is being used all over the world by different groups for collecting information, and it's only going to explode scientifically. It's amazing for people interested in environment and conservation. It's amazing. The other thread, that sort of theoretical interest, is, and this relates to Brad saying I'm controversial. I'm never controversial. But you know, what does everybody say about nature? They say it's fragile. You know, that's like the knee-jerk reaction. Fragile desert, fragile coral reefs, everything's fragile, right? Everything is fragile. And come on, you're biologists. Your kids aren't fragile. Your kids are resilient. You know, there's not a reason to have the knee-jerk reaction that everything's fragile and you know, a little bit of damage does and it can't recover. But there's a real value. I understand the political reason. Because if you say an ecosystem is fragile, then you draw a line in the sand and there's no negotiation. It makes all subsequent discussion clear-cut. But if you sit there and say, well, we actually don't know. It could be fragile, it could be resilient. It's kind of an open question. It varies from place to place. It makes it hard to draw a line in the sand and inform decisions with science. So we started building this database where this started with colleague Michelle Marty and I, and looking at massively damaged ecosystems. So not just clear cutting, spills, oil spills, bleaching events for coral reefs, and collecting data where you have before and after measurement. Basically, you have a perturbation and what happens to the perturbation. So how would you measure resilience? Just great tool, Data Thief. If you never used it, it's a wonderful tool. Anybody here used it? No, it's fun. So resilience index. It's basically the decay rate of the perturbation. You measure the perturbation and you see what happens to it through time. And the decay rate of the perturbation is a measure of resilience. All perturbations don't decay, some of them grow. And it's dimensionless, which is good because you're going to scale at different time scales of the thing. So just building a huge database on these resilience indices, and we, you could ask questions like, are larger, more severe perturbations harder to recover from? Does generation time influence recovery or resilience? And you could ask about the magnitude of the perturbation. This is just one plot. Resilience index, magnitude of the perturbation. The magnitude is the percent. Is it a percent? And there actually isn't any clear relationship about the magnitude and the resilience index. You can look at different types of perturbations. really good one, interesting one that's striking, and then we go to people who work at the reefs, they know this is true. This is from bleaching in Pacific versus Caribbean reefs. And the Caribbean are all clustered together, but in the Pacific, there's a wide range, and there are some Pacific reefs, Papua New Guinea, some places like that following a bleaching event or something like that, recover really fast. And there's a lot of hypotheses about why that may have happened, and some that are really hammered. And so you can go in and try to understand that. Theoretically, though, to me the interesting question is, as we started, so we've had this data for a while, and now we've only written one paper on it so far, but as we try to analyze it and think about it, we sort of realized that we were, to a certain extent, we were locked into a certain conceptual framework, and I think this is the conceptual framework for ecology, to a large extent. And that's, you probably, any of you done modeler or ecosystem and community ecology, you've seen diagrams like this, high stability, low stability, high resilience, low resilience, you have marble, and this is high stability, because it's hard to rock them out of there, and you view perturbation as moving the marble along this way, or tipping the board, like that. But the reality is, when you actually start looking at data and trying to understand it, I mean, in other words, you look at each different study and you see what happens to perturbation with different metrics. I think, and this is what I don't think we have any climate change on it. And this is what I think is a theoretical challenge. The reality is the world we live in now is changing directionally, and it's changing directionally because of climate and human development. It's not like there's a basin, you're just sitting there. There's directional change. And what you're really asking theoretically is, what canyons of future will ecosystems go through or a species go through? That makes you write models differently and interpret models differently. I think it makes evolution much more important. Because it's no longer about keeping things the same. It's about, the change is unavoidable, it's happening, and really the question is, can you have any predictability about what factors tell you where this model goes? Well, the classical analyses of community matrix models and eigenvalues and all that, this doesn't do that for you. It doesn't get you there, much of the classical community ecology theory. And so, where am I going with this? I'll leave it open for questions. So I've sort of came, why am I interested in coming back to a university? Although, have you figured out how your budgets work here? I asked myself that. Universities have the most bizarre budgeting system. I work for a company, an organization now, run by a Goldman Sachs guy, and it is so crisply clear, and it's so beautifully transparent. So, universities are different. But what you do have is you can ask these types of questions, which I can't ask now because of the nature of my job. I think this ecosystem service tool and model, the way I look at the world, is not going to go away. It's only exploding. But it's settled on a modeling framework, and everybody does it, nobody's questioned it, of land use, land cover, as the input data, and everything flows from there. I think that could be a fundamental mistake, and be failing to take advantage of a higher quality data that is soon going to be widely available like in 5 to 10 years. And so you ought to anticipate that and go back and rethink how you're going to do ecosystem service modeling. You got to do that in a real place. My favorite habitats are Patagonia and Cambodia. And sort of develop it a little bit more from first principles. I think, I'm aware of empirical paper. I think resilience, I know that in some sense the word is terrible because it means different things to different people. You really can't use it without giving it a quantitative definition, and yet nobody ever does. That's why I gave it a quantitative definition, the rate at which a perturbation shrinks or grows. Not to mention this, but You could argue with that. But out and about in the world of policymakers and the general public and NOAA and agencies and cities, when they ask about the environment and what scientists in ecology and like ecology and evolution could tell them, what they want to know is about resilience. You know, Bloomberg's and Rockefeller Foundation's Resilient City thing, NOAA's, if you look at NOAA's strategic plan, resilient communities, that's what they want. You know, they've all realized that there's this change. And so that the job of ecologists is not to manage and keep things the same. The job of environmental managers is to do that. But they have a very vague notion of resilience. Very hard to make it, to tie it to any science. And to tie it even to experience. I know that you know, people have done, you know, asked questions about how do individual species respond to perturbations as a function of the genetic variety. And you can do that, and that's a cool thing, and that's useful. How do you build on that? How do you build on that? I think that's incredibly important, and that's a challenge to the threshold paradigm. You know, what so much policy debate gets framed as there's an absolute threshold, 2 degrees. And we have to avoid that because after you exceed 2 degrees heating, you know, all hell breaks loose in the climate. That's a very different paradigm for science. The paper, I think it just came out this morning, I'd seen it in galleries, about boundaries and ecosystem boundaries. I actually don't think that's the right way to think about it. I don't think it's useful. I actually think that it puts you in a policy mind to think about it that way. I think it's much more useful to think about it as you have to manage systems for change and resilience. And I think that's both a deep theoretical and empirical challenge to do that. And it requires a lot of opportunity for grad students and postdocs and people with a lot more creativity to be. Why don't I end there and I'll take questions. Thanks.
Questions?
Victoria.
Wonderful talk. This is great. Love all part, lots of parts of it, lots of ideas. But at various points, really, there's a common underlying theme of this is how do we do, first of all, how do we do good science that's actually making realistic predictions? And how do we do it in a way that leads us to a way to implement a policy that can make a difference? And I guess the big question I'm going to have, because I see this, that framework of the science-based policymaking, often it does clash with environmentalists, and not radical environmentalists, but you know, I can give you a few different kinds of examples where I've given talks, for instance, to explore when does habitat fragmentation disrupt gene flow. Sometimes it does, sometimes it doesn't. And I think that's much more useful than just saying, oh, we can't fragment because of this. Right, so you do it, and then you have a group in the audience who are very upset with you because you just, you know, oh, you're playing into their hands. And so there's that kind of thing. The other experience is like when you have a bunch of people who are willing to rally around one tree, one oak tree, and put hundreds of thousands of dollars in it, and they could take that hundreds of thousands and preserve a whole area. And when I argued or talked with a colleague at NRDC, you know, they're going for that, you know, that oak, that's signature oak that's losing there, and that you can put a person in the tree because a road is going to get through. That tree really isn't going to do anything. And in some ways, so I think we haven't all settled on, you know, what is the right, so what it seems like to be a politically great idea, put somebody in a tree and protect that one tree and spend hundreds of thousands of dollars to then move it, when maybe what we need to educate people is we need to be spending that kind of money to think about where are the right kinds of parcels that will enhance the resilience of an overall ecosystem. So I'm just throwing out some problems and obstacles and opening up for some reflections on those, because your talk is saying, let's go for good science.
And I have certainly experienced what you described, and so I think there's a lot of, and this is where policy analysis goes in. There's a game theorist at, that a friend of mine introduced me to that I'd like to work with more, who on this two-degree thing, as an example. A game theorist who asked the question, what's the effect of setting thresholds in policy and having uncertainty around it? And when you apply game theory to it, the effect of having thresholds with uncertainty around it is that inevitably you will never get an agreement to cut emissions. If instead you have a dose-response curve with uncertainty around it, you can get coalitions of agreements to reduce emissions. So I think there's actually room for, I don't know if that, it was a beautiful idea, I love the theory, I don't know if it's true, but it made me think. So I think there's room for a lot of scholarship to ask, scientists can be pretty dumb about how they intervene in policy. Because they can do beautiful science and then say, well, we got to make it simple. We got to have a nice negotiating principle, so here's what we're going to deliver to them. And it has absolutely the opposite effect of what they hope. And so I think one answer to your question is there needs to be much more research about that translation of the science to the impact on policy and what works and doesn't work. That would be one answer. Another answer is that what you described is true in a lot of settings, but there also are settings that behave pretty reasonably. And it's sort of the most rewarding place that I've worked is Mongolia. And why is that the most rewarding place that I worked? When World Bank went in, after they got their freedom, they had their economic class when they got their freedom from Russia, instead of building infrastructure, they sent Mongolians to Oxford and Cambridge. They didn't build infrastructure. There's still no roads there. They didn't build infrastructure. They spent it on education. And it was actually a conscious decision, a strategic decision the World Bank made. So you go to Mongolia now, and we went over there, and we taught a conservation biology class, short one, just 3 or 4 days, to about 20 or 30 members of the parliament. There's 76 members of the parliament. And it was real. Now think about that. And so, I wouldn't want to teach a class out of Congress, but I could imagine a worse set of students. And so then, their engagement there is, they've written a law about offsets for their mining, which is so you got to do. And now they're in saying, well, how do you decide really what the offset is? And so it goes to questions like your tree and so forth. They're going to do this thing. How do you use the science to quantify the impact on, they care about grassland productivity, they care about herbivores, they care about water. All those things are scientifically tractable. And then how do you turn that into real science-based policy? Well, they have a culture that will do it. And so you look for the bright spots, which are, maybe there are a few bright lights in the global map. But you hope that if you could make it work there, then you could really illuminate it. In the US, where are the bright spots? Cities. Because cities can behave more rationally than states. And states can behave more rationally than the federal government because of the way politics work. So you look for the bright spots.
Let me know if this is off topic, but I'm interested in your thoughts on the sustainability of conservation in the light of the changing global economy, because as conservation organizations and NGOs buy land and set it aside for preservation and conservation, they're ultimately removing value in changing local economies. And so I'm curious what you think of that in terms of a future world with 10 billion people.
Well, so in reality, I can speak for the Nation Conservancy. We do a lot of private land conservation. We do a ton of it through easements, which are legal, and even in China, we do easements, conservation easements in China, which are in the U.S. they're in perpetuity. In China, they're 50 to 100-year contracts. But they're legal contracts that restrict uses on the land. But they allow some uses. So most of our land transaction now is easements on private land. That does not take it out of the economy. It leaves it in the economy. And it can be very, very effective. You may be aware there's a paper in forestry that's really interesting that Jack Putz published about selective logging and what happened to biodiversity in that. There was a meta-analysis, and it showed, I mean, it had an impact. The selective logging had an impact on the biodiversity, but much less than you might have expected. So that's sort of my, not threshold, not line in the sand, sort of understanding, but we don't have the science. We have a deal that will become public, I hope, in a couple of months. But it involved a situation, a giant private land transaction. I think it might be the biggest ever. And the person who wants to put their land into conservation believes in wind power and wants the license for it to be called conservation lands but have wind energy generated on it. And then what fraction of what footprint could that wind energy have on this horrific land? Now, we don't have the science to answer that question. But this fellow is amenable to us generating it, and if that comes through, we'll fund the science. And we'll write the terms so that if the data came in and you had to change the terms, there's a provision for it. That's pretty, see how that could work? So you could write into an easement, a contract, that it could be changed based on new data. That's not the way it's done normally. No, the classical easement is just fixed. But that's a way of starting to make it. So I see private land conservation, the fact that it's growing in China, Argentina, Chile, it's actually a good model. It's a very good model. Cool.
I'm curious about how the ecosystem services and that modeling those parameters, how that is playing a role for your clients. And you showed us that slide with 3 scenarios: the biofuels, subdivision, the forest, and ag.
They use it, so we've been very successful, and we haven't done as good a job. We're doing a writing workshop in some nice place in Northern California, and this is Stanford, and me in Minnesota, it's the NACAP. We're doing a writing workshop where we're trying to write up that, like, how is the information being used? We call it use case studies. And we want to write them in a really, some of them will be written for scientific papers, some will be written for magazines to tell those
Yeah,
stories.
you decided they don't want the bottom line, but there's a big hero
Right.
represented. So I'm just curious what they think, how would they?
In that particular case, they picked the sort of agroforestry, not the development and not the biofuels. And that was the outcome. But
You guys have some data on how that is playing.
we have enough to be able to start writing these things, yes, yes. And we've done a poor job because if you think about it, the postdocs do the research and they move on. And then the follow-up, you know, who does that? So.
I want to get back to the time to the threshold timeline and your deliveries and setting all of the doses. So the behavior you deal with continuous life.
Rebecca's right.
But is that really realistic when you deal with issues that you don't know?
Right. So I think there are real threats. I mean, so obviously, like epidemiological models, this classic threshold, there's no, you know. But in I think other cases, I think there's been, I could provoke you because you won't mind. There's been an affection of theoreticians for thresholds because they're interesting, you know, it's like little bifurcations and stuff like that. So there's been just a kind of a, you know, just an affection for those types of effects because they're really interesting theoretically to examine. And sometimes that's gotten too zealous. But it is real. I mean, it's real in meta-populations. So there are places where it's real. It's real in meta-populations. All epidemiology is real. So there are systems where it's real. And in those cases, it's also useful policy-wise. How do we set policy? It's very useful. But it's just not automatic. If you read these boundary papers, you know, the global boundaries and so forth, I think it makes it a little bit, it's really just something that's a comfortable narrative. It's not something that's
Perhaps the thinking is to identify value and actually use this idea of story.
right. Yeah, so there are professionals, for sure.
Peter, I guess my question is more about
how your modeling and other efforts address the issue of motivation, human motivation and interest in these questions. I mean, one of my concerns is that as we become more urbanized, people are less and less have genuine knowledge of nature and the environment, and it matters less to them what happens to them. I'm really concerned about that, and I wonder how your models are informed by the changing landscape and human thought about conservation.
That's not in my models. And nor do I think it's easily put in my models. But we do think about it. There is an empirical question here.
Yeah.
I have a ton of data that nobody's ever analyzed. I tried to open it in a public database where the Nature Conservancy has failed initiatives. And I think we win on 95% of them. We have a standard scientific approach. You do a focus group, standard focus group at a professional type. It's actually been the same professional consulting firm that's done all our initiatives. And then we do a stratified random survey, 1,200 in the state, phone calls, 30-minute phone calls. And we have data, amazing data. We use it to inform the language that leads us to a 95% and raising $50 billion of public money for conservation. We don't use it to ask interesting theoretical questions. We just use it to find the words to put in the campaigns. And it's an incredibly rich data source. Because you could even, you could, the spatial right, I mean, you could use it. The other really good source is Flickr data, which we do have a model, of recreation that uses Flickr data as georeferenced. And so you can take your photos and use that data to see how people are using the natural landscape as a measure of the value of so there's news, there's, but and just the whole,
There's a lot of cloud computing applications where you could use some of this information.
And I think I actually, sort of textual analysis, doing text analysis of things, which I don't know how to do, but I know when somebody knows how to do it. So there's, human behaviors, those questions are amenable to study both quantitative and qualitative. And I think that's one of the most interesting things. How do people, I don't think your story is, I think what conservation biologists say as a knee-jerk reaction is, oh my God, everybody's urban and they're disconnected from nature. It's an easy story to tell. I'm not sure of that. I'm not sure because there's still, I'm just not sure. I mean, you read writings and things like that. You read, it would be fun to, you might look at all the teenage, all these big popular teenage books that are read, because when my kids went through this stage, they read them all. They picked up a fair bit from that. So, who knows?
It's something to think about.
Yeah.
So,
somebody else is going to think about that, not me, because
so my knee-jerk reaction, and this sort of feeds on what Steve said, is that I've always thought the whole kind of ecosystem services model for really high-end conservation, for motivating state parks, national parks, and super protected areas, I've always thought was just ridiculous, because I don't think that's why, maybe it's the flip side of what Steve's saying, I don't think that's why we have the Endangered Species Act. I don't think that's why we have National Park, Service. I think that's for a certain very kind of elite class of conservation ethics that people care about. But then there's like the rest of the planet, where the question is it going to be in trees or is it not going to be in trees?
right, there's working landscapes, you might call them.
Yeah, and there, I can very much see the economic models and the ecosystem service approach. And so, I mean, in your view, are there these kind of two discrete things, or should the ecosystem services, however it's done, in a quantitative way, without lines in the sand, should it apply to everything?
No, it shouldn't. Obviously, it shouldn't apply to everything. But the real hardcore ecosystem service models would say what you just described as cultural values, and they have methods for reflecting cultural values in their model, so they're not that good. But so a certain, you know, a certain set of ecosystem services would say, it still works everywhere, you just describe a cultural value. But I get the point you're saying. The real point you're saying is, you know, looking at those services I put out there, that really are amenable to biophysical or biological modeling.
Right.
And what is it comfortable with us? Do they justify big nature reserves? Maybe a little bit for water, where there's and where there's a downstream city that has wealth, and there's an upstream forest, and you can, the Condor Reserve in Ecuador, Condor Bioreserve is an example. But that's because that was never at threat of being developed, it was at threat of being used for cattle raising. And so you could make a link between get the cattle out of there, or else you're going to have nasty water. And you could do that for a real Condor Reserve. So there was just a report called Urban Water Group. It takes either 500 or 100 largest cities. Do you know what it is? Have you seen it?
Yeah.
And it tries to connect where a city gets its water to upstream places. And in maybe, I can't remember, not that many of them, but maybe in 20 or 30% of the cities, you could make a significant argument that doing large-scale conservation
But
upstream.
that still might be managed forests, that might be national parks.
Right, but it's pretty easy to make it or not. I mean, it's still pretty
You
easy.
could do it as a national park, but as long as you could do it as something else,
Right.
where you also had some extraction or whatever, then it doesn't motivate national parks. Right? It doesn't motivate wilderness
Right,
areas.
right. So what motivates that is what I would call some law of nature, or whatever. But, you know, one person's nature is, what one person calls nature and loves changes from person to person.
Okay. Thank you.